Now the glycolytic system, as the term implies, is going to use a carbohydrate, essentially glucose, to produce ATP through a multi-step process. It goes in two ways. Actually, it really goes in one way. It's just the rate is actually going to be different. So fast glycolysis is going to move more rapidly. Slow glycolysis is going to move more slowly, as the term implies. The difference will be in the end products. Fast glycolysis will turn over so rapidly it won't really be able to get into the aerobic system, versus slow. It will have some opportunity to do so. So the end product during fast glycolysis is going to be lactate. When we look at the chemical reactions, we see that the last step is going to be the production of pyruvate. However, in the presence of oxygen, we'll shift the enzymatic reaction to acetyl-CoA, which is the precursor to Krebs cycle. But if it happens too rapidly, then lactic acid is going to be built up and accumulate inside of the muscle cell. Now, if it gets to go slow enough, oxygen will be present in large enough quantities, thereby allowing pyruvate to go into the mitochondria to be used in Krebs cycle. So fast glycolysis used to be called anaerobic glycolysis, and slow glycolysis used to be called aerobic. And that's due to what happens with the end product, pyruvate or lactate. However, if you investigate the chemical reactions in glycolysis, oxygen is not a component of glycolysis. So it's sort of a misnomer to say anaerobic versus aerobic, because glycolysis does not require oxygen. It takes place in the cytosol, so it does not take place inside of the mitochondria. Therefore, it is completely anaerobic. It's just what happens to the end products. They can either be continued into the aerobic oxidative system, or it can be built up as a byproduct and potentially inhibit muscle contraction and some other things. So as you can see here, we start with a molecule of glucose or muscle glycogen, which is obviously produced by multiple chains of glucose. And after we get past fructose 6-phosphate, it divides into two pathways. So although we get a gross yield of 4 ATP because we require ATP during this chemical reaction, our net yield is only going to be 2 ATP. It takes 2 to make it. We make 4. Our profit, so to speak, is going to be 2. Okay, so why do we call it lactic acid? The byproduct is lactate when it's fast glycolysis, and you'll notice that on either side of the split reactions we have a release of hydrogen ions. Those hydrogen ions can only be picked up for transport and move into the mitochondria if oxygen is present. Basically, we call it opening the doors. So if oxygen is present, it allows the NADs to carry those hydrogen ions into the mitochondria, which we'll see can be converted into energy. If it's not, there's an accumulation of hydrogen ions, and it's an inverse logarithmic scale known as pH, little p, big H, and as pH declines, it's because of the increase in hydrogen ions, hence the term lactic acid, because it's an acidic environment. So why would it turn over fast versus slow? It all has to do with how the body is requiring the use of ATP. Like in the phosphagen system, if there's an immediate need, we're going to use an immediate source. Similar with glycolysis, it'll turn over more rapidly because we'll require greater amounts than the ATP phosphagen system can supply, and we'll need it more rapidly than the oxidative system can supply. Therefore, the need for the fast glycolysis. The downside, as we said, fast glycolysis, the byproduct can be lactic acid, and in very high amounts, that's that sensation you feel, that burning sensation. It's an acidic environment, and it actually inhibits muscle contraction. Once we stop exercising, we can shift that into the blood, and then lactate will go to the liver through the Cori cycle and can be converted into energy. And this is just a slide showing that process. So it's too acidic. We can't metabolize it in the muscle, so we dump the lactate in the blood, and it will transfer it to the liver. And through that Cori cycle, we can metabolize it and actually convert it back into a form of useful energy. So although we say it's a toxicity in the muscle, it's toxic because it inhibits muscle contraction, but we can actually use it because lactate is very similar to pyruvate and can be interconverted, therefore be able to reproduce that lactate into a form of glucose. So with slow glycolysis, because of its rate of turnover, that'll be based on the demand for ATP. In other words, your muscles aren't contracting at high rates of speed, at high forces or high powers, so it allows for the oxidative system to be part of this process. When oxygen makes it into the cell, it essentially allows for transmittal of the end products of glycolysis to move into the mitochondria. So as you can see here, those carriers of the NADH and the pyruvate will make their way into the mitochondria, and then it initiates the oxidative system, which will be Krebs cycle, also known as the citric acid cycle, and the electron transport or the electron transfer system. As in control of the phosphagen system, control of glycolysis is also going to be based on a feedback mechanism. Turning over glycolysis will be promoted during intense muscle activity. ADP, inorganic phosphates, ammonia, AMP, and slight changes in pH. Remember, if pH is too dramatic, it actually inhibits everything. So it's inhibited by high levels of ATP. Again, similar to the phosphagen system, high levels of these particular compounds mean that there's sufficient amounts of ATP. The rate of glycogen breakdown to glucose, so depending on how fast or how rapid we need to turn that over. And then we have a limiting step called phosphofructokinase, or PFK, which is actually inhibited by pH levels. So this graph is just showing the difference between a trained person and an untrained person. We have two major situations where lactate is initiated, and then also where it starts to accumulate in the blood and becomes problematic. So we look at lactate threshold and trained versus untrained. There's a little bit of a difference, and then when we look at the onset of blood lactic acid, which is the point of no return. So that's where you start accumulating so much lactate inside of the muscle, and that's where the inhibition is going to take place. Through training, we can respond better. We can work better in that acidic environment, and in fact we create more of an acidic environment because we've been capable of producing more fast glycolysis, and so training allows us to do better in that environment. So the oxidative system is aerobic, or requires the use of oxygen. So when we look at the chemical processes for these oxidative systems, you'll see that oxygen is going to be part of the construct. So it requires molecular oxygen. Remember, with glycolysis, there was no oxygen in the equations, so it did not require oxygen, hence the term anaerobic. It provides ATP during very, very low intensity requirements. So when you're at rest and not doing anything, your predominating energy system is going to be the oxidative system. It predominantly uses carbohydrates and fats as your substrate, and especially at rest, there's a shift towards the utilization of fat. And actually, as a result of training, you can improve your fatty use of substrate during training to help spare glycogen, which during an athletic event, glycogen is actually the number one limiting factor in a marathon run, for instance, because you can actually deplete and run out of muscle glycogen but you can live on the production of ATP from fat sources, well, basically for days. People go without eating.